Great, so thanks very much. Sorry I can't be there. I hope the Alps are nice and the hiking is fantastic. So I think the chair from the last talk was saying the title of the talk is Categorical Symmetries in QFTs. You could have said this for this talk. I will try to connect these category things to symmetries actually in quantum field theories, and also give some applications that are more physics motivated. But let's get started if we can. So most of this is based on work in collaboration with my amazing postdoc, who will now be also Royal Society URF in Oxford, Laksha Bharadwaj. There are 3 papers, 2 are out. The 3rd one is coming soon. Can you see actually the hand here when I'm pointing?
Yes.
Yeah, okay. And then also some follow-up applications with my 2 students, Leah Bottini, who many of you will know, and Daniel Payer, who is a new student of mine. And then there's lots of related work that we've done with also Jing Chang and with Apoorv Tiwari. Okay, so the whole physics connection to these higher category, fusion higher categories, really starts off with studying what physicists refer to as non-invertible symmetries, for lack of a better name. I don't know who's to blame for this, but it's some of these people in the first 3 papers, I think, some of which are in the audience. And really this started in the last 2 years now, a huge sort of development of constructions of these symmetries in QFTs. Here's a selection of papers to do this more quantitatively. Most of the contributions to this growth here in this graph, that's the citations to the original generalized global symmetry paper, really come from these non-invertible symmetries. So there's something going on in terms of the connection of QFTs to these higher fusion categories or non-invertible symmetries. So basically, the starting point for this connection is that we identify topological operators in a QFT with symmetry generators, right? So this is absolutely the core connecting point. And we take topological operators and then we interpret them as symmetries. So for this first generalization to higher form symmetries, these were still sort of higher codimension topological defects for which generate some group-like symmetry, GP or gamma P. And here I will always denote the topological defects by D with a subscript that is the dimension of this defect, and then it has some label. Here it's a group label, and so they fuse in this case just like a group dictates. So this gamma P is some finite group, for example, and then these DQs would fuse in this way. So one mild generalization is to higher groups when all these different dimensional topological defects start talking to each other, but the non-invertible world is sort of going away from groups to algebras. But of course, in this particular audience, saying algebra, you probably be shot down. So actually, we should say it's some fusion higher category that will now play the role of what actually the topological defects generate. And so many examples exist, of course, in 1+1 dimensions. So in 1+1 dimensions, the Verlinde lines and 2D rational CFT have some non-invertible fusion. This is this sort of standard Verlinde type expression. So these topological lines fuse with these fusion coefficients in a RCFT. But also in 2+1 dimensions, where we have these MTCs, where they have topological, tensor, modular tensor categories. But really, the key new developments happen in 3+1 dimensions. So the examples there are really starting with, say, the simplest of gauge theories, a U1 gauge theory, Maxwell theory in 4 dimensions, and we gauge the charge conjugation. You can generalize the other outer automorphisms. And then there are these duality defects, and then, of course, condensation defects. So this is sort of just a selection of different types of non-invertible defects that we've seen. And I'll focus on a particular subclass today, but just to sort of outline what is known there. And all of these have really, realization in QFTs. This is not just sort of mathematics for the sake of it. It really realizes these in, say, an O2 gauge theory in 4 dimension, a pin plus 4n gauge theory, etc., or in these cases, in 40 Young-Mills theories, for example, 40n equals 4 to Young-Mills at special coupling values. Okay, so what is the plan of my talk? I'll start with categorical symmetries, and the key role that I'll sort of or the key player that I'll introduce. Many, I think, have talked about this in the last 2 weeks in the Stockholm meetings. I don't know how many speakers have been in this conference yet on this, but the SIM-TFT, so the symmetry TFT, how that characterizes these categorical symmetries. And then in the second part, I'll talk about generalized charges and how that connects to the SIM-TFT. And then at the end, answer Konstantin's question from Matt Bullimore's talk, like, what is this all good for? And to give you some applications to actual physical problems. Okay, so please ask me questions. I should be able to see the chat and we'll hear you. Okay, so let's go to the first part. So very loosely speaking, we'll be looking at categorical symmetries from a physicist's point of view. What this means is we're looking at topological defects of a certain dimensionality, starting at, say, d-1, and then going down all the way to d0. And so they would then form a set of objects. So top layers, then the d-1 dimensional ones will be the objects in some d-1 fusion category. And then the lower levels are the n-morphisms between these. I'll focus very much in many of these examples on fusion 2 categories. And they were, of course, famously discussed by Douglas and Reuter. And there we have objects that are topological surface operators. So in a 3-dimensional quantum field theory, they would generate a 0-form symmetry, and 1 morphisms are topological lines, and then 2 morphisms, local operators. And so we can have 0 form, 1 form, 1 form, 0 form, and potentially also 2 form and -1 if you like, but let's forget about the -1 form symmetries. And at each layer, you have a fusion structure and a composition of these types of defects. So this is just to remind you, you don't have to focus for the 2 categories on 3-dimensional QFTs. That's maybe the most natural thing, but you could also just say a 2-dimensional topological surface realizes a d-3 form symmetry, subsymmetry of this, of a higher dimensional d-dimensional QFT. And then the 1 morphisms are the -2 form symmetry, etc. So this is applicable also in higher dimensional QFTs. It's just in 3 dimensions, this is all that you'll have. Okay, what are examples of such higher categorical symmetries in QFTs? Of course, the standard higher form symmetries fit into this framework, and those are the d-1 sort of vec G categories. So G is some finite group, and this category is basically has the top layer, which has group-like fusion. So you have these d-1 0-form symmetry generators that fuse according to the group law. And then all the lower dimensional ones are sort of trivial topological defects on each of the layer above. So we can gauge here if there's no anomaly here. So here you could also put in an omega, so some co-cycle, some anomaly. So this would actually then potentially obstruct gauging G. And if there's no anomaly, you can gauge all of G, and then you get to the d-1 rep G categories. And those are then usually have, in fact, in all cases, will have non-invertible defects whenever D is bigger than 2. So even for D goes to 3, so when you have 2 vec, we'll have already non-invertible surface defects. In this case, even G is abelian. And I'll get into this. I think yesterday was a question, what is a rep Z2 and 2 rep Z2, and I hope this will be answered. And of course, some of you will be bored to death about this, but then hopefully some other parts will be more interesting for you. So we start with a 3D QFT with a 0-form symmetry, say it's group-like, and we're looking at a Z2 0-form symmetry for simplicity. And then the categorical symmetry will be 2 vec Z2, and the fusion will be basically D2G, G and H fuse according to the Z2 group law. And so this is an invertible symmetry. Now, what happens when we gauge the Z2? As I will get to 2 rep Z2, and usually gauging the 0-form symmetry, as a physicist, you would think, I gauge a 0-form symmetry, I go to a 1-form symmetry, a dual 1-form symmetry. So I would have topological lines that are labeled now by the Pontryagin dual group in this case, so by Z2, and they generate a 1-form symmetry. But 2 rep Z2 has more than the topological lines, it also has topological surfaces. So in fact, in 2-rep G2, we also have these condensation defects, where we take a two-dimensional, the trivial defect, and then gauge the one-form symmetry on this two-dimensional subspace. So, and these have fusion that is non-invertible. And I should be writing this down. I'll write down the fusion for these momentarily. So of course, in mathematics, this kind of gauging is extremely well understood, but for physicists, we like to do this very explicitly. So in fact, writing down, you start with a zero form symmetry, the topological defects, D2G, and now you gauge G, and then actually determining all the fusions is an extremely satisfying thing for a physicist, and to actually see this realized in the QFT. So there's essentially two ways to do this. One is using sort of what a mathematician would do. You look at the bimodules for algebras in this 2 category, and that was done also by the Durham group and then also in our paper. But a slightly more intuitive, physics-motivated perspective is you could start with this theory that has this G symmetry, and then stack GT QFTs before you gauge. And these GT QFTs then become sort of frozen into the symmetry, so they become part of the symmetry, and in fact, they become topological defects after the gauging. And so in fact, for the simple example of what I alluded to here in this 2-rep Z2, those are precisely the condensation defects. So just to explain this a little bit better, so if you have, say, a 2-dimensional topological defect, and you would like to actually now stack this before you gauge a global symmetry G. So you have a theory with a global symmetry G, a zero-form symmetry. Then what I'm going to propose is we'll get these additional topological defects in the 2-rep G category by first stacking with these 2D GT QFTs and then gauging the diagonal G symmetry. And then these 2D GT QFTs will actually become the condensation defects. So for this, we need to know what are these 2D GT QFTs. So finite number of vacua, basically they're just TQFT, 2D TQFTs are just the number of vacua, and they have very simple fusion. So each vacuum has some operator, trivial operator identity I, J, has a multiplication delta J. And we also have sort of interface domain walls between these vacuum, and they fuse according to this law here. So in fact, what this becomes is just a category 2-rep. So we have these TQFTs, they're just labeled by N, and Tn times Tm is Tnn. So this doesn't have yet this G structure. So if you actually have 2D GT QFTs, we have two things how to actually include this G symmetry. One is we can actually put a G SPT phase. So that's an alpha cocyclone H2GU1. Or we can also now look at actually spontaneous symmetry breaking. So in this case, we just have a single vacuum and the G symmetry is completely preserved. And for multiple vacuum, we can have a breaking from G to H. So H is some subgroup. And then basically the set of GT QFTs are just determined by the subgroup, and then some kind of two cocycle that's valued now H2 of H with U. And so a generic TQFT will then take this form. A GT QFT will take this form here. So when I now gauge in the say, for example, 3-dimensional theory with a zero-form symmetry G, before I do that, I stack on top of it a TQFT of this type, and then gauge this. And then these TQFTs then become topological defects. I'll label them exactly as these TQFTs. So D2H alpha will be precisely that arising from this TQFT T sub H alpha. And they then become topological defects in the gauged theory. And the fusion is determined in this way here. This is sort of a general formula for this. But in the specific case for the Z2 case, we can show, for example, explicitly in a moment that this actually will become a very nicely simple fusion that is non-invertible. So for G equals to Z2, we have H equals to 1 or Z2, and alpha is trivial. So it couldn't be simpler. So the TQFTs are basically IDF2 vacuum. So this is the defect that I'll call B2 minus that's associated to H equals to 1. So that's completely, in this case here, there's a non-trivial TQFT, and then there's a TQFT which is 1 vacuum. And so that's the identity defect. And now the question is how to actually compute the fusion. You can use this general formula here, but we can also just look at, how the tensor plot of these vacua behaves. So the identity fuses in this way, of course, and with the D2 minus, it just gives D2 minus. And the interesting fusion is this fusion of the defects, D2 minus with itself, where you get this 2 times D2 minus. So this is precisely what you can recognize if you know condensation defects as the fusion of condensation defects. And so these topological surfaces, then there's also a story for the topological lines and the operators, forms this 2-rep Z2. So even though G was abelian and everything before in the 2-vec Z2 category was completely invertible, after gauging, we get a 2-rep Z2, which has these non-invertible surfaces. Okay, and so this is just a comment that this is exactly in this particular instance the same as the construction using gauging of the one-form symmetry, the dual one-form symmetry on topological surfaces. So the condensation defects. Okay, so the structure now of this 2-rep Z2 is we have this 2-dimensional topological defect, D2 it, D2 minus, and then there's sort of these also lines, which I didn't discuss, but this is basically the structure of this 2 category. So general lesson is if I have a 3-dimensional theory with a 0-form symmetry, and it has a subcategory that forms 2-vec G, and then we gauge G, then we get sort of a symmetry category, just 2-rep G. Okay, and of course we can apply this to, actual physical theories, like for example, 3-dimensional SO4N theories, so gauge theories are particularly nice examples. So here we'll start with 2-vec now of the group D8, and that actually will be a completely invertible symmetry, which it's a non-abelian group, but still there's a D8 invertible. Every element has an inverse, and now we can gauge the D8 if there's no anomaly, and then this gets us to the pin plus 4N gauge theories, and they have a 2-rep D8 and non-invertible symmetry. There are also these intermediate stages we can gauge subgroups, like a Z2 times Z2 or the Z2. So here, this is the outer automorphism Z2, and then we get sort of these non-invertibles or something like a 2 group. So there are also these intermediate stages. And so in this way, you get from starting, say, from something that is a purely group-like symmetry in a 3-dimensional gauge theory to a whole web of different types of 2 categories, 2 vecs of higher groups, or 2 reps of finite groups. And that sort of story then extends to higher dimensions, where we can, again, in this class of spin 4N or SO 4N gauge theories, map out the full sort of web. Now this, in practice, becomes an extremely laborsome thing. You can imagine gauging now all these things and determining the fusion of all these things, and it's extremely sort of case by case. So one question is, how do you actually find a more unified perspective on all these categories? And this is sort of where this SymTFT comes in. This is sort of one utility of the SymTFT. So all of these different perspectives on these different gauged versions, some of them are invertible symmetry, some are non-invertible, some are higher groups. All of these actually come from a single theory, just imposing certain different boundary conditions. And so that's what I want to explain in the next couple of minutes. So the symmetry TFT has a somewhat murky history. I don't know really where we should be associating it to, but certainly Gayudo Kalp had some papers. It goes also back to papers in Comments Matter by Ji and Wang and I think others. They're more in the context of topological order. Really here we're interested in these from a symmetry perspective. And I think that was more done in the high energy community, but the idea sort of percolates throughout those fields. And of course, in mathematics, as we'll see in a moment, this will connect to the Drinfeld center of this higher fusion category. So in fact, there's also some history. Okay, so what is the idea? Basically, different choices of these global forms, so these kind of complicated webs of different gauge-related symmetry categories, in fact, come from the symmetry TFT. It's a topological field theory. If you start with a quantum field theory that is d-dimensional, then the SymTFT is d plus 1 dimensional, and the key property admits a gap boundary. And all these different global forms are essentially choices of different gap boundary conditions. So usually we'll draw this in this way here. So we have, we start here, there's a theory in d dimensions. It has some topological defects. They fuse in some particular way. It can be higher fusion category. Symmetry can also be just an invertible symmetry. Whatever it is, I'll just denote by cal S. And now we can sort of gauge that symmetry into a d plus one dimensional SIM-TFT. So this is the Z of S. And it has two boundaries. One is a gap boundary. This is the B sim. That's where basically all the symmetry related aspects will be localized. And then there'll be a physical boundary, and that may or may not be a gap boundary condition. And so all of this here is topological. And so in fact, we can slam it back together. We can do the interval compactification. We can sort of squish the sandwich and go back to this d-dimensional theory. Right, so the key two properties is there's this gap boundary and here's this physical boundary, which may or may not be gap. Examples are like the Torah-Vero theories that we heard about in the last talk for fusion category symmetries. And there are lots of applications. And one really important way that the SIM-TFT will feature in the second half of the talk will be in terms of the symmetry, the generalized charges under generalized symmetries. And that was already actually observed in this paper here, that the symmetry TFT would actually play an important role for that. So, and then of course, for higher fusion categories, is there a question? No? Okay, so basically the second part will be focusing on not just studying different symmetries by imposing different gap boundary conditions, but actually looking at the topological defects of the SIM-TFT, and they'll actually furnish the generalized charges. And Matt in his talk alluded to that as well from a slightly different perspective, using this tube algebra, which I will not use at all. I'll really simply just look at the symmetry TFT and its topological defect as the generalized charges. Okay, so how do we construct the SIM-TFT? As I said, we start with the symmetry, and the symmetry determines basically the SIM-TFT and the gap boundary condition B sim. And that's completely independent of what the theory was. Now, the actual theory depends on, you know, the second boundary condition, the physical boundary, actually depends on the QFT that we're looking at. So if you have two different QFTs, indeed, the boundary conditions will be different. But the crucial thing is, when you're studying the symmetry properties, that determines basically already this half of the problem. And now gauging some symmetry on this B sim is basically changing the boundary condition. So if we have two symmetries S and S prime, and they're Morita equivalent, so we can gauge between them. So do one of these complicated exercises here, then indeed their centers, the SIM-TFTs are the same. So in fact, you then fix Z of S, and all you're changing is the boundary condition. Okay, so let's look at some examples. By the way, when did I start? I think it was half past, just half.
3.
Huh?
33 minutes past.
Okay, so we are being extremely precise. Very good. All right, so the first example is just an extremely basic example that everyone will know, is also appears in a lot of applications. It's just a SIM-TFT for P-form symmetry, say Zn. Then we have these background fields for this P-form symmetry, so BP plus 1, and the dual field, del Zn valued fields, and we can write down the SIM-TFT just as a BF type theory. And now these topological defects of the SIM-TFT will be these P plus 1 dimensional or D minus P minus 1 dimensional defects are just usually I integral B or C. And now the topological boundary condition is just essentially saying, do I impose Dirichlet or Neumann on the particular topological defects in the bulk? So for example, right, I can impose Dirichlet boundary conditions on these P plus 1, and then they end on the symmetry boundary. And if these C guys actually are Neumann, so they project parallel to VSIM, then they actually become the symmetry generators. So in fact, the picture is when you have a bulk topological defect and you simply project it parallel to the symmetry boundary, then they actually become part of the symmetry of the interval compactified theory. If we do look at the other defects that actually end on the physical boundary and on the symmetry boundary, they're essentially charged operators. So say a p-dimensional, the operator in the theory that is charged under a symmetry will then become this p+1 dimensional operator that has these Dirichlet boundary conditions on those physical and symmetry boundary. So of course, it can also be these twisted sector boundary, twisted sector operators. We'll discuss them in a moment, so that there could be some additional defect attached here, and we'll get to that momentarily. But that's sort of the basic story, and that's certainly what happens in this BF theory. Okay, so now how do we see the charged? So the property that, in fact, this object here is charged under the symmetry. Well, one thing is that due to this BF theory, these two operators, they have a non-trivial exchange relation, which is determined by the linking of these p+1 and d minus p-1 dimensional surfaces that are where these operators are defined. And so, in fact, because this is non-zero, if this is non-zero, if they actually link in the d+1 dimensional bulk, then the associated defects will also link on the projected onto the symmetry boundary, and so then that will determine the charge. Actually, this is really best explained in terms of picture. So here we have the symmetry guy. So this comes from a parallel projection onto the symmetry boundary, and this is the charged operator, and this is precisely saying that there's a linking between this OP and this topological defect, and we're calculating the charge on that. So this is really the picture just in these abelian simple BF theories. The general story is much more complicated, but it's just to sort of to set the scene for how we should, why, in fact, it's a totally sensible thing to conjecture that these topological defects in the SIM-TFT will, in fact, correspond to both the charges, but also furnish these symmetry generators. Okay, so let's actually go a little bit more towards these some more interesting symmetry structures. So let's look at the SIM-TFT for some of these d-1 back G. So for abelian G0, this is just the same story as before, but really we can label these generators. So now I say it's the Drinfeld center. Well, as you may have guessed, if you have a fusion category symmetry in the theory, then in fact Z of S is precisely TQFTs whose topological defect is the Drinfeld center of that fusion category. So in the case of abelian G, these defects basically are labeled by a group element and a representation. And so this is just what you would expect for that kind of fusion category. And that's sort of agrees with also this BF discussion we had earlier. For non-abelian, this becomes much more interesting. So in fact, we have topological defects in the SIM-TFT that are labeled by conjugacy classes G and a representation of the stabilizer group HG in this conjugacy class. So for D equals to 2, this Drinfeld center topological defect basically is just a sum of rep of these stabilizer groups. And in fact, this is true more generally. So in fact, the Drinfeld center for a d-1 back G has a decomposition into d-1 rep HG. And there can also be additional anomalies. So they would then decorate these reps. So one interesting observation is by Thibault de Coppet, basically in D equals to 3. So if you have two fusion categories, in fact, all of these are Morita equivalent to 2 vac G with some omega, so some anomaly, times some mod B. So there's a modular category of some non-degenerate braided fusion category. And in fact, the Drinfeld center of that, right? So any one is basically, you can gauge it, so it becomes one of these. And now the Drinfeld center of this is basically simply the Drinfeld center of this 2 vac G omega, because it's trivial for this mod B. So you just get in the sum of the T2 rep omega G HG, and this is the general answer for the D equals to 3 case. So in fact, for D equals to 3, studying the properties of these type of SIM-TFTs will be sort of solving the problem in that dimension. Okay, so what I actually want to, there are examples in our part 2 paper for this 2-vec, as to general centers of 2-vec G and how they, how this talks to symmetries and generalized charges. I actually want to go back to 2 dimensions and discuss an example that many of you might find sort of relatively straightforward, but actually does some interesting applications. So I'll need this to prepare for the last part of the talk. So let's look at a 2-dimensional theory with some S3 zero-form symmetry and just ask, how does the sim-TFT actually look like in this case? So this is just calculating the Drinfeld center for vec S3. And there are papers in math, there are papers in condensed matter that do this. And the reason why I'm presenting it is because I'll later on have a nice application that I think brings in sort of this connection with physics. Okay, so G is now S3, it's a symmetric product of Z3 and Z2. And I always write sort of the Z3 elements in terms of A and A squared and so on, and B is the Z2 generator, and these are the relations. Now what we'll need is the representations, so the irreps is the trivial, the sign, and then there's a 2-dimensional irrep for S3, as well as the conjugacy classes and their representations. Right? So the conjugacy class essentially is the identity, the full group A, and then basically B. So, and these have representations which are so the usual roots of unity 1 and omega squared and the sign. And so then the topological defects of the sim-TFT. So these are now topological lines. They're labeled by the conjugacy class, and now this representation, in this case, you've got 1 minus an E for the identity 1, and then for the A and B conjugacy classes, the representations are just those. Okay, so this is basically the structure of the topological defects of the symmetry. Starting from this, so for abelian groups, it's relatively straightforward to see how we go back to which boundary conditions imposed give back the vec G symmetry. In the case of S3, this is slightly less obvious. It's still rather straightforward, but you have to sort of study the specific Lagrangian algebra and actually study the boundary condition. Anyway, so indeed, so the symmetry boundary is now fixed in terms of the possible Lagrangian algebras. So basically, if you're asking what are the possible B sims in 2 dimensions, there's sort of a very nice, very concrete formulation for this. Basically, they're classified in terms of the Lagrangian algebras. So you solve a condition, you take a general linear combination of these topological defects, and then satisfy certain algebraic conditions that are related to the dimension of this algebra and the dimension of the fusion category. So basically, it's completely sort of computational. So in this case of Z of vec S3, the Lagrangians, so I'll label them just by conjugacy class and rep. There are 4 Lagrangian algebras. Yes? Is there a question?
I don't think so. No.
Okay. So essentially, this is these are the 4 Lagrangians. There's 2 which give rise back to something like vec S3, and then 1 with 2 which give rise to 2 types of rep S3s. For higher fusion categories, there's unfortunately no such thing. So in fact, you cannot write down a simple criterion for Lagrangians that, say, in a higher category, it will tell you this is the set of algebraic conditions you need to solve, and then this determines a Lagrangian. But there are many examples from concrete computations. But that's a one drawback, which would be nice to actually understand better. Okay, so this is essentially saying if I now have these topological defects in a Lagrangian algebra, and they basically will become the lines, the topological line that can end, then that determines a B sim boundary condition and thereby a global form. And all of them are gauge related by going back, for example, to the sim TFT, then changing the topological boundary condition and recollapsing it back, or by gauging the symmetries. Okay, so this is how the symmetry TFT encodes symmetries and all these different gauged versions of symmetries. And what's perhaps more interesting as an application is that it also encodes actually the charges. And we've seen sort of this a little bit in this BF theory already, and that's what I'd like to discuss on the following. So essentially, we're starting with the question, if you have a symmetry, what are the charges under that symmetry? And for group-like symmetry, it's just representations. So this is extremely well established. But for non-invertible symmetry, or higher fusion category symmetries, this is was not clear. Even for the case of the invertible symmetries, this statement here in blue is actually not the most general thing. So this is sort of the first, perhaps interesting insight that, in fact, already starting with invertible symmetries, the representations of G for a finite group G, that's not the full story. So in fact, if you define basically the charges that are Q-dimensional to be Q charges, then in fact, you can also have higher Q charges for, say, a zero form symmetry. So in fact, what we sort of showed in this part one paper is basically that indeed for even invertible symmetries, there's a slightly more refined story where these higher representations come in. But the one message, if you want to take one message home, is the Q charges basically for symmetry, that's a Q plus one that has Q plus one dimensional topological operators, Q plus one. Basically, these are the genuine, so the untwisted and twisted sector operators of the SIMTFT. So the SIMTFT topological defects are the Q charges of a theory with the symmetry S. And in fact, when you change now boundary conditions, you're changing what S is, but you're not changing what Z of S is. So in fact, the set of topological defects stays the same. So what you're actually just reshuffling is who is twisted sector, who is untwisted sector. And we'll see that concretely in examples. And this statement, this sort of connection between topological defects of the SIMTFT and the charges is sort of in the case of the invertible symmetries, in fact, more than just saying that they're representations. So that actually the statement becomes that they're actually higher representations. So in terms of the SIMTFT, what we'll be seeing is that there are these topological defects, right? So before we had just this defect spanning between the BFIS and the BSIM, but now they can also sort of connect to another topological defect. So it could be twisted sector or untwisted sector. And what we'll see is that all the topological defects will have a role to play in terms of these higher charges. So for invertible symmetries, as I said, the statement is already more general than just saying that it should be p-dimensional operators for p-form symmetry, the transformative representation of GP. So in fact, Q charges basically for Q-dimensional genuine operators on the p-form symmetry group. In fact, it's nice to generalize it to a P group. So in fact, you have sort of 0 form, 1 form, and so P minus 1 form symmetries. Then in fact, the Q plus 1 representations of this higher group. So the simplest sort of generalization is that for 0 form symmetries, you basically get the Q plus 1 reps of the 0 form symmetry as charges of the as higher charges. So Matt in his talk discussed this from this sort of tube perspective, but really we'll see that this comes also from this more general SIMTFT statement. An example, so it's nice to also see this not actually realized in terms, if you take a 4-dimensional QFT, you can ask, well, is this sort of a sensible statement to make? So in fact, for the one gauge theories, again, the simplest possible for the gauge theory, they have charge conjugation, and that acts as a Z2-0 form symmetry on the theory, and you have the 1 form symmetries, and now we can ask, are they actually not interesting higher charges? So a Q charge is a Q-dimensional operator that transforms in these under the Z2 charge conjugation symmetry, and it's relatively straightforward to see how. So the 0 charges are just local operators. So the gauge field transforms under the charge conjugation, A goes to minus A, field strength therefore goes to also F goes to minus F, so that's a 0 charge. The 1 charges are simply Wilson lines. So we have electric Wilson lines, magnetic Wilson lines, Toft lines, and they go for WE, charge E, Wilson line will go to W minus E. So in fact, they will form, these two form a non-trivial 1 charge. I'll specify in a moment what exactly the associated higher charge is. And there are also two charges. So there are these topological surface defects, which are the Gluck-Witten operators that generate the one-form symmetries. And again, they're written in terms of the field strengths in this way. And so, in fact, they actually go precisely into each other in this way. So they also transform under the Z2, and they'll actually furnish a 2 charge. So you already seen the simple example that this notion of higher charge may in fact be a sensible thing to consider. But I haven't really explained to you yet why should this be sort of a higher 2 rep of Z2, for example, right, the 1 charges. So I want to explain a little bit more why 2 rep of G actually is sort of now characterizing 1 charges for 0 form symmetry that's invertible. Was there a question? So I can hear sometimes some noises, but I don't think these are questions. Okay. So let's look at 1 charges for 0 form symmetry. So we have a 1-dimensional operator. That's, the question is, how does a 0 form symmetry act on this? Well, it can send it to another, so this line operator to another line operator. So basically I have a codimension 1 wall that's the 0 form symmetry generator, and it pierce that, and there could be another line operator coming out. So in this sort of setup, we can have now at this intersection, basically along this line operator, we can have a certain induced symmetry. And in fact, if you look at the stabilizer, so all the H's that sort of fix this one line operator, and call this H sub O, and in fact, that's sort of the induced 0 form symmetry on that line operator. And so in fact, the question is, now if I take these 0 form symmetries on this line operator and fuse them, do they have to fuse in terms of just a group like the group G? And in fact, they don't. They can have also a non-trivial phase here, sigma HH prime, where sigma is an H2 of H with U1. So this precisely is this type of 2 cocycle that we've seen. So in pictures, basically, we have this line. These are the local operators. And now we actually, when H is in the stabilizer group, then this fusion may be true up to this phase sigma. So in fact, there's a cocycle. And so this particular 1 charge is then characterized by some group H, a subgroup. That's the stabilizer group. And again, this 2 cocycle. So in fact, H comma sigma, subgroup G sigma and H2 of HU1, that's precisely what we said is sort of the set of 2 reps of G0. In fact, the 1 charges in this way are exactly the 0 form symmetries. The 1 charge of the 0 form symmetry is precisely the 2 reps of G0. So there's one nice physical way of seeing why these higher representations actually come into the story. Okay. So for Z2, right, the 2 rep Z2, we looked at what that is. There's this row 1, which is basically H is 1, sigma 0. And there's a row 2, which is H is Z2 and sigma 0. We can find very nice QFT applications where these are realized. So for example, this Maxwell theory, right, these are basically W alpha, the Wilson line with charge alpha, before I call it E, and W minus E are based in the same orbit, and basically form this 2 representation row 1, 2. And only for these fixed values, when alpha is 0 and pi, actually you get this row Z2 one. And similarly for spin friend, there are interesting, nice high representations. Okay, so I wanted to talk about, because my son gave this talk about these symmetry fractionalizations, I wanted to explain that a little bit, how that fits into the picture. So there's also a way of thinking of these symmetry fractionalizations in terms of these higher charges and how that fits into the higher charge picture. I don't think I have time for this, I'll just skip that. And you can ask me later. So what I actually want to get to is the last part, which are these IR applications. So just the summary, basically we have a symmetry category S, some fusion higher category, and the 2 charges of the symmetry are basically Q plus 1 dimensional topological operators of the symmetry FT. Yes, and so again, just to emphasize, they stay the same under gauging. It's just how different genuine, non-genuine operators are identified in the actual physical theory. And of course, there are loads of examples in 2D, 3D, and 3D and 4D that one can now look at. So in the last part, I want to discuss applications. And Konstantin yesterday asked Matt, what is it good for? And Matt's answer was, I'm not really sure. And so I want to basically clarify that there's a real utility in studying these things. I will not go into the higher fusion category sort of applications of this. There's a story for this also for the two fusion categories. And I'll actually start in 2 dimensions and just focus on so fusion category symmetries, and essentially use the generalized charges and the SIM-TFT picture to study certain types of gap phases in 2 dimensions. So we start with a fusion category symmetry S. So this is this work that's going to appear soon with Leah and Daniel, and also with Lakshya. So consider some fusion category S, and then using the SIM-TFT, we can basically answer a relatively general question, which in many cases the answer is known, but this sort of way of answering it will allow us also to generalize it to higher dimensions, and it connects it to the SIM-TFT. And I think there are some implications which at least we couldn't find in the literature. So there's some new results that we hope we can also contribute in this particular 2-dimensional world. So what is the asymmetric, what is the set of asymmetric gap phases in 2 dimensions? That's sort of the question to which we will have an answer using the SIM-TFT picture. So group symmetries is basically just sort of the Landau paradigm of how you sort of classify symmetry breaking phases. So for example, if you have some Z2 group symmetry, you can give a charged operator, a local operator, VEV, and basically then you have spontaneous symmetry breaking, and that tells you that you'll have 2 vacua, for example, in the IR. So you start in the UV and you have a operator that's charged, and then you can infer that in the IR you'll have 2 non-zero vacua that are mapped under the Z2. So one question you could ask that's quite natural in terms of these fusion category symmetries is, how does this generalize to non-invertible symmetries? And there's much related work on this already, some in the high energy physics community, some in condensed matter. And so here we'd like to put a sort of SIM-TFT perspective on it, which then allows us to go also to higher dimensions. So the main idea is basically, so far in the SIM-TFT, we had a topological boundary condition on one side, and that's where the symmetry was localized. And then there was a physical boundary, and that usually was some physical quantum field theories that was not topological. There was some 4-dimensional gauge theory or some 3-dimensional gauge theory. So here the idea is basically we also slam on the right-hand side, the phys is now also a gap boundary. And so after we do this interval compactification, we get some TQFT, and that TQFT will know about the symmetry, and there'll be a symmetry sort of protected TQFT. And essentially what this means is we now have sort of the same set of boundary conditions at our disposal on both sides of this SIM-TFT construction. And so this picture, of course, will generalize in higher dimensions, but in fact, in 2 dimensions, we can concretely already get some nice results. So the operators basically in the UV carry some generalized charges. They come from the topological defects from the bulk. And so they're associated with some Lagrangian algebras, right? So they're the ends of some topological lines in 2D. And if these charges are present in the IR, basically then tell us about the non-zero vectors in the UV. So this is basically connecting the charges with the possible phases on the vacuum structure in the IR. So essentially it is about now classifying Lagrangian algebras for these Z of S and TFTs. And of course, not every topological line can appear necessarily in some Lagrangian algebra, right? So this sort of the setup will tell you that certain lines will not actually be sort of endable. And so in fact, when you have an operator that doesn't appear in a Lagrangian algebra and that picks up a VEV in the UV, then in fact the IR won't be a gap phase. And so you can in that way also get access to gapless phases. Okay, and this is now where we go back to the rep S3 or the vec S3 that we discussed earlier. So one nice non-invertible symmetry are these representations of non-abelian groups, finite groups. So the rep S3 has the same SymTFT as the vec S3 that we discussed earlier. So this is just a reminder for you. And essentially gauging the S3 now maps this from a vec S3 where we had topological lines that were these ones here that were ending, right? So they were just the representations of the S3. So these are the local operators. These are the untwisted operators for the S3 symmetry. And then there were twisted sector operators that had non-trivial conjugacy clauses that attached to topological lines. The maps, now these topological defects, which had very well-defined, vec S3 interpretations, to now rep S3 operators. And what changes is now who is a twisted sector operator and who's non-twisted sector operator. So for example, these guys here, the Q1, 8R, that were untwisted become now twisted sector operators. So they're attached to R lines. And they're sort of nice, particularly nice illustration of non-invertible symmetries, mapping between twisted and untwisted sectors and putting them into multiplets, which is precisely this Q1A. In fact, Q1A with the identity, with the trivial representation, has two operators. One is a genuine operator and one is a non-genuine operator, so a twisted sector operator. And so those two are actually in one multiplet. So really here you see at work the SymTFT, how it maps these different topological defects depending on the boundary condition into different sectors, twisted or untwisted. So one question is, how does actually the symmetry act on the particular multiplets here? So of course here we know this vec S3, it's just the representation theory of S3. But for rep S3, it's a bit more interesting. So for example, this E topological line, so rep S3 has this representation E line and acts on this O plus local operator in the following way. So omega is again this third root of unity, and so it maps it into O plus, but then also this sort of twisted sector operator. And this twisted sector operator 1 minus attached to O minus basically maps to O plus and to again itself. So in fact, this is quite a nice sort of illustration of how these actions of non-invertible symmetries really mix these twisted and untwisted sector operators. And if you now close these diagrams, if you loop this around, right, you'll get precisely also these tube algebra pictures. But here they really come directly from the SymTFT construction. So now the question is what actually the symmetry rep S3 symmetric gapped phases. And so for these, we need to look at the Lagrangian algebras. So this is just a reminder what were the Lagrangian algebras for this Drinfeld center. So in this case, again, it's the same as the vec S3 ones we just copied from earlier. And so now the question is, what do these actually correspond to in terms of the rep S3 symmetry protected phases? So what we find is that each one of these will have sort of a particular type of symmetry breaking pattern. So there's one which is the rep S3 spontaneous symmetry breaking, and one is a Z2 spontaneous symmetry breaking. So that's basically an invertible part of rep S3. And then there's the non-invertible part of rep S3 spontaneous symmetry breaking. And then there's the symmetric phase, which is just a trivial phase. So there's just one vacuum. And then each one of these has 3, 2, and 3 vacua, whereas these two are actually distinct vacua. So you might think there are 3 vacua, maybe they're the same. In fact, here there's a very nice sort of observation that here this 3 actually is 2 plus 1, where the Z2, the remnant Z2 actually acts between the two and leaves this invariant. In fact, there's also a relative Euler term between these two vacua. So you can get extremely refined information and distinguish each one of these vacua in terms of this non-invertible symmetry structure. And of course, the nice thing is that this applies now to any fusion category symmetry you like, and most of us like the Ising model. So the Ising model being sort of a non-group like, so it's not Morita equivalent to any group like vec G type symmetry. So it's the simplest example of that type. So we can repeat the whole analysis in this setting. So the Ising fusion category has these topological lines 1, P, and S. P generates a Z2, and S is the non-invertible line. So S squared is 1 plus P. And there's basically there are two multiplets. There's a 2D multiplet, which again mixes a twisted sector and untwisted sector. So it's very similar to what we discussed in the Web S3 case. And so I can just call this the 1 plus P exchange multiplet. And the Z2 just acts by sort of a phase, so as minus or plus on this. But the S, so this non-invertible line, acts in the way that we know very well, right? So this comes from a paper, I think, by Engel and Christoph, and I think maybe Fuchs, right? You pass the local operator through S, and then it attaches a P line. And in fact, so this basically is exactly exchanging the twisted and untwisted sector operators again. And now finally, we can go and look at the single Lagrangian algebra, which is basically 1 minus and this 1 plus P exchange topological line. So this is this thing that this combination here. And so again, repeating sort of this type of analysis we showed earlier, what this gives is, in fact, there are again 3 vacua, and it has again a split like 2 plus 1, like in the case of the S3, Rep S3 example here. It's very similar to this, but it actually is distinguished by this by the relative Euler term between this 2 vacuum, this 2 plus 1 vacuum is actually different. So in this case, it's square root 2. In the other case, I think it's 2. So basically, the symmetry acts in this way that actually you get these additional sort of factors that then tell you that, in fact, you can still distinguish the 3 vacuum theory that has this 2 plus 1, right? The 2 are exchanged by a Z2 from the one that appears in the Rep S3. And so this actually you could now call sort of the Ising spontaneous symmetry breaking phase with 3 vacua. And it characterizes it again uniquely in terms of all the data that are specified here. Okay, so let me conclude. Basically, just a few comments. What I was discussing in this 2-dimension in the last part is, of course, now something that we'd like to extend to more group-like, but also non-group-like, like more general Tampa-Yamagami type fusion categories, and then also the extensions to higher dimensions. Let me just summarize what the main points of the talk were. So the SymTFT basically captures the symmetries. It's of invariant under Morita equivalence. So symmetries that are gauge related have the same SymTFT. And so it sort of unifies that picture of these gauge related symmetries into one structure, just changing sort of the boundary conditions on the topological side. The topological defects of the SymTFT are the generalized charges. And in fact, they contribute to both twisted and untwisted sector operators, depending on the boundary conditions. And then finally, we can use this setup not just to study symmetries of, say, QFTs, but actually also TQFTs that are symmetry protected by some categorical symmetry as well, because those are precisely connected to topological defects that don't appear in these Lagrangian algebras. Okay, so thanks very much. Are there any questions?
Any questions? Yes.
Would heckle a little bit as expected.
Sure, yes. I mean, I quoted
like
you here.
We like is to separate the definitions from theorems, I think, just for clarity. And for us, I think the SymTFT is a definition of topological symmetries in the quantum field theory. So the paper we wrote was exactly to give this is how it defines topological symmetries in the QFT. I don't know another definition of topological symmetries for which you could assert a theorem that it's the same as the other picture.
I think this is an agreement, right? So topological the symmetries are precisely captured by the SymTFT.
That's a definition, so, which is okay. It's fine. Just not a theorem that.
Oh, I see. So you're saying what I was talking about here earlier is sort of harping on a definition rather than showing anything at all. Fair enough. It's just that as a physicist, you like to actually also then see what actually concretely this entails. Like, how does this higher fusion category symmetry, how is it realized in a particular QFT? How does it act? How does it relate under the gaugings that we're familiar with? These type of questions. But then actually, I think you're absolutely right. The more interesting, or at least I think the more interesting point is that also gives rise to the charges, right? That actually really adds some additional physical input. I don't think that's a definition of, you could also say this is the definition of
the charge,
okay.
but that's just my ignorance. But no, I was going to get to the serious, there is a serious question you can ask here. Because you can define topological operators internal to a QFT. We don't know how to define fully local topological operators into a QFT, but let's be optimistic and assume that notion existed. You can ask, is it true that you can generate them all from a well-chosen D+1 dimensional TFT? And that is, I don't know, there's an answer to that question. So that would be
Yeah, so you're saying, is it true that, for example, here I can get all of the asymmetric gap phases? Is this sort of one sub-question of the question you're asking?
Yeah, sorry. I missed a
Yes?
few words. Can you repeat what you just said?
Is what you're saying, it's the question, so a way of phrasing the question in this particular context here as, how do you know that this generates all possible gap phases, for example?
You know, let's say all possible topological operators internal to a given QFT. Is there some procedure to find that? It's not.
No, because the input, right? I think the philosophy here is you start with a theory with a symmetry, right? So that's the input into the problem, right? I don't start with a theory and I ask what is now the SymTFT. I say the theory with a symmetry, then you can construct this D+1 dimensional theory, this DQFT. So I don't think there's a claim that it constructs this, you know, given that theory T, it constructs automatically for you the symmetries. The symmetry here is always the input.
We agree. I just pointing out that's an open question.
That's an open question. Sure, absolutely, yes. And I think that's probably an extremely hard question. Right, if you give me an arbitrary quantum filter in D dimensions to determine all of the possible symmetries, it'll also contain like continuous symmetries, space-time symmetries. So I think that's a pretty hard question. Yeah. Are there any other questions about the talk about?
I can't see any other questions. So thank you again for your wonderful talk.
Okay, thanks.